In today's video we want to take a closer look on a JRM1 wing, take a completely new approach in designing it and printing it on the Bambu Lab with the new PLA AERO. So let's start.
In our endeavours to reduce the weight of our JRM01B version of our VTOL jet, 3D printed jet, Renee and I looked at different ways of lightening up the structure, the internal structure, and having a review of the print infill patterns available to us through our 3D printers. And due to the popularity of the Bambu Lab printers, we wanted to investigate and see whether we could come up with some wing profiles that were feasible as well as structurally sound, all printed on the Bambu Lab printer. As of August 2023, Bambu Lab introduced their new PLA offering called PLA AERO, which is a low density foaming filament used in the aero modelling community for lightweight construction. Lightweight PLA is a relatively difficult material to 3D print, and so there are certain settings required on the Bambu Lab printer to print PLA AERO, and the following shows some of the investigations I went through to understand and harness the capabilities of the Bambu Lab printer to print some lightweight 3D wing profiles. Here I've imported a 3D step file of the JRM01B trial wing. This is the engineered pattern with the engineered surface. I'm hoping to do the setup here in Vase mode. I prefer to step import because the quality is much higher than STL, depending on your STL settings. Bambu Slicer allows that to, or Bambu Studio allows you to import step files cleanly. So in this instance I've imported the step file of this wing. I have a preset for my actual printer, which is up the very top here. Bambu Lab AERO preset for 0.4 nozzle. I've called it the MPV AERO settings. Main change has happened at the extruder with the retraction length 0.2 Z-hop while retracting 0 Z-hop type slope, and those settings for the remainder of the print settings for the printer. Then down here I have prepared a Vase mode preset. So in this instance the quality is under the following settings here. We have the main changes, seam position at the back. We'll have the tolerance or the slicing resolution here set and change, arc fitting, classic wall generator, and inner to outer infill, which doesn't seem to make a difference in this instance because it will be Vase mode. Strength, these are the settings for wall loops. Sparse infill, of course 0%, ensure vertical shell thickness. I do tick this on and off sometimes to see if that makes a difference in terms of the final sliced model. That can be adjusted. The main adjustment and the main change here is the speed settings. I have gone across the board 35 millimeters per second on all the editable fields. Normal printing here also 35, and the outer wall 35. So this means that we'll save that preset. This means that when the printer follows the profile of the wing in Vase mode, it will maintain and not accelerate and decelerate, because it's the acceleration and deceleration that I've learnt affects the quality of the laid down layer of PLA. Of course, no support in a Vase mode, and then under others we've got skirt loop 0, no brim type, and even odd layers. Bi-layer is the print sequence, and spiral vase, and the rest is settings for time lapse. And the most important thing down here, reduce infill retraction, ticked. So when we slice the plate, you can see it does a very good job of slicing this geometry, and of course as we slice through it and see and pass through all the layers, we can see it has a very clean line or lay down pattern in the Vase mode. What I try to also do is show the travel paths up here in travel under line type. Is a great way to check to see that the path of the print head is tracing correctly through the product. Here I've imported the very basic wing model, no internal reveals or hollows into Bambu Studio. I still have my machine settings at MPV Aero. The major settings here are now in my Gyroid infill preset, and I can just scroll through here to show you the settings for my Gyroid infill. Under strength, the main focus here is the one outer wall loop. It's important that this outer wall loop is a single one due to weight, but also the quality of the outer wall will be affected by a twin wall if it's in foamed PLA. We have the 5% gyroid infill and infill combination to detect narrow internal solid infill and ensure vertical shell thickness. Under speed, again, as the previous settings for Vase mode, I have 35 millimeter per second speed across the board. No support under support settings, and under others, no skirt loops, no brim type, even odd slicing mode, print sequence by layer, and reduce infill retraction. So when we slice this part now, I've turned on paths, travel path, and you can see here displaying the travel path. We can look at flow rates throughout the wing profile. We can also look at the speed at which everything's being printed, so you can see there's no acceleration, deceleration in any part of the model, which is very important. And when we go back to line type, we've got the travel, which in this instance becomes very messy on the inside of the gyroid. I'm not sure if there is going to be an update in the Bambu slicer to improve that. Another key thing here that I've turned on is the seams to see where the seam ends up on this profile. In this particular instance, on the leading edge. If we go to quality, we can actually set that to aligned. If this wing were oriented on this plate, this is the front of the plate, if it were oriented around with the trailing edge to the back of the plate, I think back would have worked. So we can quickly just check that. I'll rotate this wing through sort of 45. Let's get that on the plate there. Just move it off the danger zone. That's why I'm getting a warning. We slice the plate. It's at the back, and so in this instance it depends on how the wings are oriented in Bambu Slicer as to where that seam appears. We could have also have moved this back into its original position if it's this way that you would like to print it, possibly for time-lapse viewing. Then aligned seems to resolve the seam and puts it onto the tail end or trailing edge of the wing. So that's an important thing to keep an eye out for. And then as we slice through the part, you can see the travel paths. For some strange reason, Bambu Slicer forces the head to travel right across the body of the part, as opposed to going along the walls and following the gyroid and then returning back and then doing the outer profile, which I would have thought would have been a much cleaner tool path. In this instance, you can see the gyroid infill gets rather messy. It's the way one of my wings printed, so I was very happy with the outer surface. It was critical that I got this travel path shown, because on one model I had printed it out and there was a lot of surface defects on the front leading edge, and as a result the surface quality became very poor. Having identified the defects on the front leading edge, I went to the machine settings, extruder, changed the Z-hop while retracting and boundary to 0, and changed the Z-hop type to slope as opposed to spiral, which solved the problem. What I tend to do is usually grab the Bambu cool plate and spray it with some 3D lac plus and coat it lightly, full surface, let that dry, and then insert back in the printer. Based on Bambu Lab's recommendation in their wiki page on PLA AERO, it is recommended to be used on the rear of the machine on the external spool holder. This, however, can cause the filament to absorb ambient moisture, which could cause problems at the tool head. it's something that may need to be tested, and you may need to check out to see which option works best for you, and it could also be highly dependent on the humidity levels in your workspace or place where the printer is operating. After numerous setups and failed starts, I eventually managed to get the settings so that the gyroid infill would work neatly. As you can see here, the internals are still quite messy as the tool head travels back and forth, but on the grid pattern design, you can see the Vase mode process was laying down filament very cleanly and very neatly, and the accuracy and surface finish was exceptional on these particular parts.
Yeah, here we can see the Bambu Lab X1 Carbon at work doing the wing in Vase mode. This is a very good way to print lightweight PLA because there is no stop at all necessary, so we don't have this problem of oozing or any differences in the forming process. The forming process is never stopped, and this is a big advantage to reach our lightweight goals.
So after a rocky start with the Carbon X1 from Bambu Lab, I did manage to find some settings and set up some profiles that worked for me and allowed me to print out the lightweighted wings from our JRM-01B project between Renee and myself.
By having a closer view to the Bambu Lab time-lapse of printing the gyroid wing, it's absolutely obvious that there is oozing between these gyroid infill, and also the Bambu Lab creates an extra wall right along the airfoil. While printing in Vase mode with these integrated ribs on the inner surface, there is absolutely no oozing visible. As next step, we integrated an aileron to the engineered wing, which was printed in Vase mode, and this get out also very nice, even if there is a gap in the outer surface. Finally, we were very happy with the result and could solve all the challenges, and the engineered wing came out better and better, and we will stay engineering this solution beside our gyroid parts. As important as the print quality and the weight goals is also the stability and technical integrity of our printed parts. And for this reason, Mark built up a very nice test stand to put the wing under bending and torsion loads.
This is the wing test jig that I've come up with based on what I had in my office and workshop. A set of kitchen scales and a Dremel press. I'm using the Dremel press with a Bambu Lab carbon fiber PLA bracket with a removable pin. That bracket can be flipped around through 180 degrees. That means we can test the wing in its normal flight orientation as well as upside down. What is happening here is as the wing is deflected through the lever arm, the root of the wing moves down, but the wing tip is forced up on this post, and that post actuates down on my kitchen scales, giving me some good readings. The reason I chose the kitchen scales, they were in grams. I did have a set of luggage weighing scales, or handheld luggage weighing scales. I was hoping to hang off those round holes in the arm, so for torsional load at the end of each arm, so at this end and that end, then vertical load, and there's also vertical load down as well as the vertical load up. So all in all, the jig at the moment is ready to test our wing sections. Try a torsional wing load test on the engineered small grid pattern wing. Applying 200 grams, 300, 400, 500 grams, 600, 700, 800, 900, a kilo, 1.1, 1.2, 1.3, 1.4, 1.5, 5.8. Bottoming out, full travel on the wing. One of the pins fell out. Now moving it to the opposite side. Zero the scales. Leading edge twist, 500, 600 grams, 800 grams, 900 a kilo, 1.2. We're getting buckling in the top surface here, 1.3, 1.4. You can see the twist, 1.8, 1.9, 1.96. And we're hearing a lot of structural damage there on the wing as it's deflecting. Reviewing the wing profile now after the torsional test. You can see up here in the leading edge here and the cap that goes on there have created quite a bit of damage. You can see when I flex the wing structure, it's separating members there. Same deal here in the nose section of the wing. But other than that, the overall profile of this fine grid structure has fared very, very well, and very impressed with this design and printing approach. Here we're going to do a torsional test on the 50% larger grid pattern engineered wing. Starting 200 grams. Start to see some twisting. This wing already had a damaged front leading edge from the previous load tests. So you can see the tears opening up there. 500 grams. You can see some real serious buckling. A lot of deflection down the rule side. Not a lot of twist in the wing. 700 grams, 800 grams, and we're seeing serious popping. 800, 900 grams, and we're starting to fail. And that was the trailing edge. Leading edge, front leading edge is starting to split. Serious noise. 600 grams, front leading edge is splitting on the first two cells. 700 grams, 800 grams, and we're getting major damage. So 800 grams is sort of the limit there. There's some serious deflection on that wing. You can see here, front leading edge totally split open across that region, indicating that this part of the wing, because it has less reinforcing structure, is unable to support the loads. But as it gets further down the wing, more cells are contributing to the strength of the wing structure, and therefore all up, still a decent result for a 30-gram wing. That is very delicate, huge spacing between the cells. A great result for this lightweight PLA AERO part. So see somewhere in the print there a bit of the missed layers, so the leading edge isn't absolutely perfect on this. Here we have the gyroid wing, and we're going to do the torsional wingtip test. 300 grams, 500, 600, seriously buckling in the leading edge here. The layers are separating from the underlying gyroid pattern. 900 grams, kilo, serious bending and flexing in this area here. 1.1, now the point at 1.1 where it's yielding and starting to fail. Trailing edge there. Leading edge test on the gyroid wing. Much stiffer, much stronger. Now this fares 1.1 kilo already. 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 8. The front section of my cap dislodged. I'll try that again. It's just being held on by friction, so we'll see if this occurs again. We're getting some twist there. 1.2, 1.4, it's coming off again. 1.6, 1.8, 1.9 kilo, and we've totally snapped front section of the wing at 2 kilo. We'll have to check back on the video first. So removing this now from the jig, you can see substantial damage, separation and delamination across the rear of the gyroid. Underside surface seems to have fared okay, but all the pressure of this cap on the tip of the wing is exactly where the shear broke, which is understandable because all the load is being transferred through the cap onto the wing and not transmitted through the rest of the structure, and the gyroid split locally and failed on this particular wing. You can also see some of the earlier damage from the load tests there. But for a 52-gram gyroid wing, a 2 kilogram loading in a torsional load on that wing is significant and impressive. Comparing the test results now of our 3 wing profiles, we had the gyroid infill 5% at 53-gram wing profile. It sustained a maximum load of 2 kilos and a deflection of 30 millimeters. Whereas the Vase perimeter printed engineered wing with a 10mm grid pattern sustained a maximum load of 2.5 kilograms with a deflection of 50 millimeters and the very lightweight 50% less grid Vase perimeter printed wing at 30 grams only sustained a 1.5 kilo load with a deflection of 40 millimeters. From this, it's quite evident that the default settings for a gyroid infill wing will be up to the task at a 2 kilogram loading. However, the engineered wing was not only lighter weight, but also was able to sustain a much heavier load and also deflection of 50 millimeters.
A link to the Bambu Lab AERO PLA you'll find underneath in the video descriptions, and also some links for supporting this channel. And that's it for this video. Have a nice week, and we see us in the next one. Bye bye.